Good afternoon, good afternoon. Today I am doing the Western Cape Government prelim paper, that is from the Metro North Education District, September Trial Common Examination. We are going to go through geomorphology. We are going to go through geomorphology. Remember on my previous video, that I've uploaded, we went through climate and weather. Now we are going through geomorphology. Let's go through the questions. Various types of drainage patterns P to U are illustrated in all the sketches below. Choose the answer and write only the letter A to D next to the question numbers. I usually do this. Reading instruction is very important, boys and girls. Reading instruction is very important because the moment you answer without following instructions, which means your answer will be wrong. So before we do anything, let's just identify this different drainage pattern. So this one is your trellis. Okay, how do you identify that is a trellis? You can see here the tributary. You can see the many tributaries are the tributaries are joining the main river at right angles. That's what makes it what? A trellis. That's your trellis. Okay. Where is it formed? Hard and soft rock. You can see now the underlying rock. So the tributaries are joining the mainstream at right angles. Then here you can see that is your radial or centrifugal, the high ground. The streams are flowing from this high ground going downwards, okay? Like the spokes of a wheel. Of course, that is your centrifugal. This one is your dendritic. Tributaries are joining the main river at acute angles, resembles the trees of the branches of a tree. This one becomes your what? Your rectangular. You can see jointed igneous rocks. You can see what is happening there. That will be your rectangular. The main river bending 90 degrees, tributaries joining also at 90 degrees. This one becomes your centripetal. This, like you've got a depression here, which means your streams are flowing down towards the lake. That is your centripetal. Okay, this is your centrifugal, centripetal. This one becomes your parallel. It's on steep slope going downwards. You can see we're starting flowing downwards. So the moment you are able to identify the different drainage patterns, then it becomes easier. So we have said this is your trellis, centrifugal or radial. This is your dendritic. This is your parallel. This is your centripetal. This is your rectangular. So the moment you are able to identify this, then you won't have any problems. Let's start now. Drainage pattern P is known as, remember, we have already said this, that's your trellis. I'm not going to waste time. In the drainage pattern, one to another in the same direction, okay? In the drainage pattern, streams flow parallel one to one another in the same direction. Let's see 2.1.2. Okay, what we have is this one. That is your parallel. Obviously, there is a word that is suggesting something here. That is your U, which is your parallel. Then the drainage pattern T is known as, where is your T? You can see your T. Remember, we have talked about this. This is your centripetal. This is your centripetal. This is your centrifugal, okay? Drainage pattern R is associated with, where is your R? That is your dendritic. What is it associated with? Uniform rock structure, which means you've got your C. Then what we have? Tributaries. The tributaries in drainage join the mainstream at 90 degrees angle. What do we have? 2.1.5, 2.1.5. What do we have here? 2.1.5. These ones, you can see, is joining the mainstream at 90 degrees angle. Okay, that is P, which means what we have there, P 2.1.5, that is your A from trellis. The stream radiates outwards in all directions from a central high point. That is central high point, which means your centrifugal, which is radial. That will be your Q. That will be your Q. Okay. That will be your Q, which is B. Then what else do we have? The underlying rock structure, drainage C. Okay, 2.1.7 at S. Jointed. It's even showing the jointed igneous rock there. So which means what do we have? Jointed igneous rock 2.1.7. That is your A. Then the tributary drainage pattern join the mainstream at acute angles. Obviously, what do we have at acute angles? We have got our dendritic, which is R. Okay. Dendritic, which is R. Okay, at acute angles and resemble the branches of a tree. 1 and 3. 1 and 3, which is 2.1.8 is what? That is your A. Let's move on. Choose the term sketch in column B that matches the statement description in column A. Write only Y and Z next to the question numbers 2.2.1 to 2.2.7 on the answer book. What do we have, guys? We have got the description here, then we have got the questions. Okay, so let's go through them. High-lying area that separate two rivers in the same drainage basin. What is important here is same drainage basin. That's what makes it an interflow. That's what makes it an interflow. If it's an high-lying area separating two drainage basin, it becomes a watershed. But the question is saying same drainage basin. So that's what makes it an interflow. Okay. Same drainage basin, high-lying area, same is separating rivers within the same drainage basin, is an interflow. But if it's an high-lying area separating two drainage basin, it becomes a what? A watershed. So the correct answer there is Y. Meeting place of two rivers, where two rivers meet, that's what we call a confluence. We call it a confluence, where two rivers meet like this. This is what we call a confluence. Then the sketch below depicts a permanent river. So when it comes to rivers, I want to highlight something. We have got 4 types of rivers, I would say. We have got an episodic, which only rains after we have received rainfalls. Okay, then we have got seasonal river, which flows seasonally. That is obviously when we receive rainfall. Then we have got what we call permanent river or perennial river. It flows throughout the whole year. Then you have got what we call an exotic river. It starts from a wetland, it passes through a dry land, okay, area, okay, like your Nile River. So what we have here, most of these rivers, the flow of the river is controlled by the position of the water table, which is the level of water underground. So what we have here, we have got water table in rain season, which means during the rain season it goes up. And we have got the water table in rain season, which means it goes down. So our water table during the rain season it goes up, during the dry season it goes down. This is why you have this river now as a permanent one. Why? Because it's flowing throughout the whole year. Because when we do not receive rainfall, the water is supplied by the water is supplied by the water table. That's basically what we are talking about, because the water table is touching the base of the riverbed. Okay, that's what we are saying. It supplies the water, which means that's what makes it not to be seasonal. But if you check here, you can see the water table in the rain season is high, but the water table of the dry season is not touching the base of our riverbed here, which means during the dry season, which means this one, that's what makes this one non-perennial or a seasonal river, because it only rains, it only flows when during the rain season. But here you see rain season is full, but the water table is touching the base of the riverbed. So it means it's perennial, it flows throughout the whole year. So the position of our water table helps us to know whether a river is seasonal or is non-perennial or perennial. It has something to do with the level of our water table, because it also supplies the water through a process of through flow, underground water that flows towards the river. Okay, so the question reads, the sketch that depicts a permanent river from the 2.2.3, that would be your Y. Why are we saying permanent? Because the water table is catching the base of the riverbed, which means this river flows throughout the whole year. You can see this one. When we do not rain season, there is no, okay, when now, it's only when we have got rainfall during the rain season. But when it's dry season, you can see now there is no water flowing here because it's non-perennial, it's not permanent. So the answer there is Y. Then the sketch below depicts, there you've got your smooth flow, that's your lamina. This one is your turbulent, which means your answer here is what? It's Y. Then the fluvial process associated with the laminar flow. Obviously, where we have got laminar flow, there's supposed to be deposition. Because the moment there's erosion, we are likely to have turbulent. So the answer there is deposition. An example of graded river, a graded river is got concave profile, which means this is your concave profile. You can see here there's a lot of nick points. Okay, on your graded profile, you also have laminar flow, which is smooth. So your answer here is Y. 2.2.6 is Y. Then change the grading of the river from graded to ungraded. When a river has been rejuvenated, which means there's change in gradient on the slope, which means it has been rejuvenated, it becomes more, it starts to erode vertically, becoming more erosive. That's the river rejuvenation. That is your Y. Let's move on to the next one. 2.3, it reads, refer to the sketches below of rapid and the waterfall. This is your rapid, this is your waterfall. This is your rapid, this is your waterfall. Of course, a rapid, obviously, we are likely to have a turbulent flow there. This is your waterfall, is even labeled. Let's go to the question. Rapids and waterfalls falls when the dominant fluvial process is where we have got erosion taking place. That's where we have got these two rapids. We find them also in the upper course of the river. Identify feature X. That's where you've got your plunge pool, which means as the water is flowing, of course, the pressure of the water, of course, is eroding this softer rock. That's how we end up with a plunge pool. It's eroding this softer rock. This is the resistant rock. So over time, just because it's eroding the softer rock, it's retreating. You can see it's retreating backwards. You can see towards the source of the river. So it means now we are going to be left with this resistant rock, which is an overhang. So over time, it won't have any support. It will then collapse in the plunge pool. That's why we have got these boulders in X in the plunge pool, because they have collapsed, of course, because they don't have any support. Okay, so let's move on. Identify, that's a plunge pool. Where do the boulders rock found at X come from? 2.3.3. We are saying the hard rock of the waterfall overhang collapses, forming boulders in the plunge pool. This is collapsing, then forming the boulders that you find in the plunge pool. Describe the physical difference between your rapids and your waterfall. What do we have? 2.3.4. Rapids, hard rock outcrops. We can see hard rock outcrops here, then soft rock. Hard rock outcrops, overlaying of here of hard and soft rock. We have got hard and soft rock. That's where we have got our waterfall. You can also see here, of course, we have got soft and hard rocks. But what do we have? This hard and soft rock, you can see that they are sort of inclined along the river. They are sort of inclined. Of course, you can see with what results there. Okay, that's basically what we're talking about. Then 2.3.5. Account for the upstream retreat movement of the waterfall, 2.3.5. So we are saying now, when you're looking at the waterfall, why is it that it's going backwards? It's okay, backward erosion. Why is it like that? The softer rock erodes, leaving the hard rock. Okay, that's why, because it's eroding, being eroded when the water falls here on the plunge pool. So the softer rock erodes, leaving hard rock exposed. Okay, that's how it is exposed to the point whereby it does not have any support, then it will fall on the plunge pool. Erosion, undercutting less resistant rock. There is less resistant softer rock here, is being undercut, being eroded backwards. Okay, then erosion, the resistant hard rock forms an overhang which is not supported by the soft rock. This is the overhang that is soft formed. Why? Because the continual backward erosion which leave these without any support. Okay, the overhang resistant hard rock collapses. That's how it collapses. We end up having these boulders in the plunge pool. That's what is happening. Discuss the economic significance of the value of rapids and waterfalls. So whenever we look at all the fluvial landforms, we are also going to write the economic value of the rapids and waterfalls. What are some of the economic value? 2.3.6. We are saying now tourism and recreation. Okay, that's what we can talk about. Generating income for local communities. We can also talk about hydroelectric power generation. Obviously, that's another thing that you can talk about. Of course, fishing and aquatic resources support small-scale and commercial fishing. Those are the three that you can actually talk about. The importance of your rapids and your waterfalls. Where we have got rapids and waterfalls, we can actually generate electricity, to be specific, hydroelectric power. Okay, then 2.4. Refer to the sketches below on river capture. River capture, guys, what comes to your mind when you hear about river capture? We have got the energetic river and the less energetic river. We have got the before and the after. Okay? We have got the before and the after. We have got two rivers here. We have got after even the two rivers. What are the likely occurrence? Okay, likely occurring in as far as the river capture. So the process first, let's try by defining river capture, a process by which one capture robs the headwaters of another, or a more energetic river captures the headwaters of the less energetic rivers. We are referring to our A as the more energetic river capturing the headwaters of the less energetic river, which is B. You can see here on Y, this B has been captured. That is river capture, river pirates. When a more energetic river captures the headwaters of a less energetic river. That's what river capture is all about. Make sure you get it right, okay? Which sketch X or Y shows the landscape before river capture? This is what showed the landscape before river capture, because river capturing has occurred now. Why evidence substantiate or supports that it has occurred? We have got the wind cap, we have got the misfit, we have got the capture river. You understand? So these are some of the things that supports that river capture has taken place. So that's why we are saying that this is before, which is your X. Which river A or B has more erosive power? Which rivers has been captured? Which one river is the capture? A is the capture river. So which river A or B has more erosive? Which means it's A. Why? Because it has captured B. You can see the after now. It has captured B. Give one reason evident in the sketch to support your answer. That is B. Of course, 2.4.3b. It has captured B. River A flows down on steeper gradient because it has been rejuvenated. The water has been added, which makes it more erosive. River A erodes headward through the watershed. So that's what is happening there. Then 4.4.4, identify the streams A and B in sketch Y after the river capture has taken place, which means we are only looking at this diagram. So identify the streams A and B. Okay, in sketch Y after 2.4.4, our A is the capture stream, We are saying is the capture stream, our A, because it has captured stream B, so it's the capture stream. Okay, that is A. Then B, you can see that is your misfit river, that is your misfit stream, that is your misfit, what? Misfit stream. So this is the misfit stream, this is the capture stream. That's how you identify the two. What evidence in sketch Y shows the river capture has occurred? In Y, what do we have in Y? 2.4.5. We have got the presence of the abandoned channel, that is the wind gap. We have got the wind gap here. We have got the misfit here. Those are the evidence. Okay. What else? River rejuvenated, okay, which means the river now is flowing at a faster speed because it has captured the headwaters of the weaker river, which means the volume of water has been increased. That's what rejuvenates the river. The size of the drainage basin also increases. These are some of the things that you can actually write about. Okay, so we are saying now the elbow of capture in the capture stream, the beheaded stream has reduced flow, which means this one has to be reduced in terms of its flow. We have got a misfit here. We have got the elbow of capture. This river has got more water now. So these are the evidence that shows that the river capture is okay. Describe the physical changes in river A, which the river will undergo after river capture. What the river undergo? Which means when the river has become more erosive, that's because it has captured the less energetic river. What will happen? The volume of the water would increase. You can see there's more water here. The volume of increase, number one. Velocity of the river would increase, which means it's now flowing at a faster speed. The increased energy, which makes it more erosive. River rejuvenation occurs because the moment it receives more water, it means it is more energetic. That's how it is rejuvenated. The size of the drainage basin also increases. So these are some of the things that you can actually include there. Let's move on to the last part now. Refer to the photo and extract below on catchment and river management. Okay? You will always have a question on catchment and river management. Please know the definition of catchment area, know the definition of river management as well. You will always have this. Workers suffer while pollution suffocates Command River. Let me read. Years of pollution and illegal dumping on Command River on the Central Business District of Eastern Cape Town of Komani, former Queenstown, are devastatingly impacting the environment and the well-being of those living in the area. The river in the Komani is filled with plastic bottles, packets, tires, refuse from illegal dumping and littering. It has obstructed the flow of water. Drains are discharging sewage into the water, adding to the problem. Just below the bridge near Sprang's Super Spa, there is a strong burnt smell from cattle, carcasses, urine, and feces. Command Hawkers Association Chairman and Kamile Faku confirmed that the stench and pollution affected workers' livelihoods. There are no public toilets in the area, and the people end up using the river to relieve themselves. The situation has been like this for the past 15 years. Okay, let's just go through the question. In which province is the Command River? Guys, you can see it's in the Eastern Cape. Eastern Cape, that's where it is. According to the extract, name 2 examples of waste found in the Command River. What do we have in them? We have got plastic bottles, we have got packets, tires, refuse. Those are some of the things that you can actually write about, okay? Explain the negative impact of pollution on Command River on the physical environment. What are the negative impacts on the physical environment? 2.5.3. Water is contaminated in the river. It contaminates the water in the river. That is on the physical environment, okay? And the natural environment. It reduces biodiversity. It disrupts the food chains. disrupts the natural flow of water. I think there was somewhere where it was written that it disrupts the natural flow of water. Let me find where it's written. Strong bad smell. I want to find out where it's written. It disrupts the natural flow of water. Impacting well-being, the river, Komani, plastic bottles, they distracted the flow, natural flow of water. That's what I'm talking about. Okay, remember it's the natural environment, so it disrupts the natural flow of water, it damages the soil, seeps into soil and affects vegetation of the riverbanks. That's what you're supposed to write about. Then the last one, in a paragraph of approximately 8 lines, suggest the measures that workers in the Komani municipality can implement to reduce. So it's a paragraph question. You are suggesting the measures and also the municipality can implement to reduce reduce pollution on the common river. So that is your 2.5.4. Your question is in two parts. Number one, of course, what can the workers do? That's number one. They can support cleanup campaigns. They can avoid dumping waste in the river. They can pressure the municipality for better waste management. That's what they can do. That is one of the parts of the measures that the workers can put in place. Then the second one, municipality, what can the municipality do? Remember, it's in two parts. You need to write what the workers can do and also what the municipality can do. The municipality can actually create buffer zones. Of course, they are trying to make sure that no polluted material can actually get into the rivers. It can be made through by growing trees along the river, so that obviously they will block the some of this waste from getting into the rivers. Provide waste facilities, regular waste collection. That's what they can do. Build and maintain public toilets. Remember, they're saying that some people are even leaving themselves in the river. What can they do? Repair and upgrade drainage systems. Run effective awareness campaigns to reduce. Campaigns to educate, obviously, on something to do with pollution. They can enforce strict laws as well. The more you pollute, also the more you pay from the companies and also from the people that are operating from around in the area, so that they try to protect the environment. So those are some of the things that you can actually do. Boys and girls, this takes us to the end of our geomorphology. Remember, it's a Western Cape paper. We have gone through 1.1 up to 2.1 up to 2.5. Please make sure, even when you are going through this video, just print a copy of the question paper, so that the moment you are listening to some of the answer or explanation, it becomes easier for you. Thank you so much. I'll see you in the next video when I'll be doing map work. That is section B of the same paper. That is the Western Cape paper. Thank you so much. Bye.